Hey guys, so in this video I wanted to go over lesson 2. So in this lesson we're going over finding imaginary solutions. So if we look at the first graph, we're finding the solutions or the x-intercepts or the roots or the zeros. So in the first graph we have one x-intercept there, which is at -2, 0. We have another x-intercept or solutions or root or 0 at +2, 0. That means if we wanted our x values of this graph, or our solutions for our x values, it'd be -2 and +2. Looking at the next graph. Don't let the gray dots fool you. The only x-intercept we have is this bottom gray dot. It's located at +2, 0, or same thing as x equals 2. Now looking at the third graph. Is there any x-intercepts? Does the graph cross or intersect the x-axis? No. So there is none or no, or whatever you want to put there for no x-intercepts or solutions. Sometimes a parabola will look like it does not cross the x-axis. Does this graph have a solution? Yes. The solution is a type of number that we have not yet encountered, an imaginary number. For each of the following, list examples of the given number system. So for real numbers are natural numbers, that are similar to 1, 2, and 3. Then we have whole numbers, that are natural numbers, but they also include 0. Integers, that would include negative numbers, 0, and positive whole numbers. Then we have rational numbers, that include fractions and decimals. Then we have irrational numbers, that would include fractions, square roots, and decimals that repeat forever. So our natural numbers, whole numbers, and integers, rational numbers and irrational numbers, all are real numbers. Now, what does imaginary numbers, what's so special about them? If we have a negative number underneath our square root or our radical sign, it becomes imaginary. Or we have this I letter, it's imaginary. We can also take this I number and add and multiply it by its other numbers. It still is imaginary. Another example is the square root of -2. Again, negative under the square root becomes imaginary. So what is an imaginary number? An imaginary number is what you get when you take the square root of a negative number. imaginary number contains I to show that the number is imaginary. This I is equaling the square root of -1. So for example, we know how to take the square root of positive numbers. Square root of 9 equals plus or minus 3. Because we have positive 3 times positive 3 gives us positive 9, and -3 times -3 also gives us positive 9. But when we try to take the square root of a negative number, like the square root of -9, we can have a real number solution. We can't have a real number solution because no real number multiplied by itself will give you a negative number. Now that we can take the square root of -1, however, we can find a solution. So for -9, we want to do a factor tree. So I'm going to take out that negative first. So I'm going to have -1 times 9. Then I'm going to take my 9 and factor it just like we did yesterday, or just like we did Wednesday. 3 times 3. -1 is prime. Only itself and 1 can go into it evenly. 3 is prime. 3 is prime. So those are my 3 numbers underneath the square root. Now my 3's, again, my index is 2 because it's not written. My 3's are a pair, so they come outside as 1. Now my -1, we just learned, if it's under the square root, it comes out as an I. So we're going to have 1 3 and 1 I, which gives us 3I. So let's do some examples. All of these are just adding the step where if we have a negative under the square root, we're bringing it out as an I. So let's look at -36 under the square root. We're going to separate it out, -1 by itself, and then the 36. Then we have 6 times 6. Then we can have 2 and 3, 2 and 3. Our prime numbers are -1, 2, 3, 2, and 3. So under the square root, we would now have -1 times 2 times 2 times 3 times 3. Our -1 comes out as I. 2 2's come out as 1 2. 2 3's come out as 1 3. So we would have 2 times 3 times I, which gives us 6I plus or minus. So for 2, 3, and 4, attempt to see if you can get the answers. Pause the video and try these 3. The most challenging one is number 4. So let's look at 4 a little bit more closely. We're going to take our square root of -49 and separate it out like we're used to. We've got our -1 and our 49. Well, what times what gives you 49? 7 and 7. You have prime numbers of -1, 7, and 7. So they are going to be under the square root. -1 times 7 times 7. Our index is 2. That is what's telling us the size of the group that we're looking for. So we have a group of 2 identical numbers, so they move out. We also know that our -1 under the square root can move out as well. So we have as an I. So we have 7 times I, which is just 7I. But then we have this random 2 over here. Well, this random 2 is going to be multiplied by whatever we got underneath the square root, or with the square root. So we have 2 times 7I. And we're just treating the I kind of like a variable. We're not going to touch it. We're not going to simplify it. It's just there. So we're going to end up getting 14I. And we have to have that plus or minus because we came from a square root and it could have been positive or negative when we had these sevens. So that is how we're getting plus or minus 14I. So let's go to the next page. We can do a few of these. Let's try a fraction. Let's do number 7. So first we're going to do a factor tree of what's under the square root. I'm going to take 144, separate it out as 12. Now, I'm going to show you a trick. You can keep going and you would get 2 2s and a 3 on both 12s, or you can keep it as 12 and you have 3 4s times the square root -1 times 12 times 12. Well, our index is 2, so we're looking for 2 identical numbers, so that moves out. You do not have to keep going if you have 2 numbers that are going to multiply itself. So now we have our -1 going out as an I as well. So there's nothing else left in the radical, underneath the radical. So we have 3 over 4 times 12 times I. So we're going to multiply this. How we're going to multiply is if we have 3 over 4 times 12, we can put an understood 1 there and multiply straight across. So straight across we have 36. In the denominator we have 4. 36 divided by 4 gives us 9. And then we have that I. Again, we're treating like a variable. Make sure you have that plus or minus out front, and there is your answer. Now let's move on to a little bit more difficult situation. Let's go to number 9. Number 9, I want to separate out the denominator and the numerator. So I want to ask myself, yes, I'm going to have a square root, but I want to take out my -1, and I want to figure out what times what gives me 1/4. Well, the numerator, what times what gives me 1? 1. So I'm going to have 1 times 1 in the numerator. In the denominator, I want something times itself to equal 4. Well, that will be 2 and 2. That will give me my 1/4. So I get 1/2 times 1/2 under my radical. Then I'm looking at for pairs of 2 identical things. My 1/2 goes out as 1/2. My -1 comes out as I. So my result is plus or minus 1/2 I. So let's try another. Number 10. Number 10, if you want to, you can go straight to your answer. You're going to have a plus or minus. Looking at your negative, I know that I'm going to have an I. For the 16, I want something times itself to give me 16, which is 4, so that's my numerator. My denominator, I have something times itself to give me 25, which is 5. You can skip all of these steps that we did in 9 if you know that both the numerator and the denominator are perfect squares, in this case they were. In 11 is just like 10 in the sense where 49 and 64 are perfect squares, but now you're having to multiply whatever you get from the radical by 4. So if we split it up, we would have our plus or minus our I. On the numerator, we have 49, so 7 times 7, so our answer would have a 7. Our 64 in our denominator would be 8 times 8. But then we've got to take this 4 and multiply it by the 7 over 8, using the same trick of putting a positive 1 underneath the 4. The reason why we can do that is because any number divided by 1 stays the same. So we're not changing the value, we're just changing the appearance. When we're multiplying fractions, we multiply straight across. So we get 28. And then 1 times 8 is 8. As a decimal, we get 3.5. So that 3.5 is going to be our number. So we have plus or minus 3.5 I. And that is our answer. So let's do one more. I'm going to go to number 20. I'm going to separate out my -8, so I have that -1 away from the 8. 8 is not prime yet, so I have to separate it out, 2 and 4. If you want to, as you go, you can circle your prime numbers. 2 and 2 gives me that 4, which gives me 2 more prime numbers. Now under the square root, I have 5 times the square root, -1 times 2 times 2 times 2. With the index 2, understood 2, I have -1 coming out as an I, and then I have 2 2's, so they come out as 1 2. The other 2 is left by itself. So I still have that 5, but now I have an I, a 2, and then the square root of the 2 that was left. And there's multiplication in between all of this. So on the outside, I can combine like terms, 5 and 2 to get 10 I times the square root of 2 and the plus or minus outside. So that would be our number 20.